Good afternoon, students. In last video, we have talked about intelligent agents, okay, in which we talked about goal-based agent. Okay, so in this chapter, we are going to revisit this goal-based agent, and we are going to focus on one kind of goal-based agent known as problem-solving agent. Problem-solving agent. So if you remember, goal-based agents act to achieve their goals. Okay, and this problem-solving agent will aim to solve their problems. Okay, and basically they use search algorithms. So they use search algorithms to solve their problems. Okay, so first we'll see the definition of search. Okay, so what is the definition of search? So search is defined as the process of looking for a sequence of actions to reach to a goal. Is known as search. Okay, so consider the example of 8 puzzle problem. So if you remember, 8 puzzle problem is a 3x3 grid where we have a tile and every tile is assigned a number. Okay, so for example, this is the start configuration of this puzzle. And 7. Okay, so now in this in order to solve this puzzle, you can move these tiles, okay, and to reach to a goal state. Okay, so in this problem you are finding the sequence of movements of these tiles. Okay, so that movement will be the sequence of actions. Okay, and whole process will be a search process. Okay, so that is the definition of search. Is it clear to you? So it is a process of looking for a sequence of action to reach to a goal is known as a search. Okay. So next topic in this chapter is well-defined problem. Well-defined problem or problem formulation. So what we are saying here, problem solving agent. Okay, so before solving a problem, you need to define the problem, and your problem should be well defined. So there should be no ambiguity in the problem definition. So we can define problem using 5 components. First one is initial state. Okay, so initial state will be your initial configuration of the problem. So for example, this can be initial state of the 8 puzzle problem. Okay, initial configuration of your problem. That is the initial state. Second one is the set of actions, set of possible actions available with your agent. Okay, so for this problem we can move a tile to the left, to the right, to the up and down. Okay, so left, right, up and down are the set of actions for this problem. Then third one is transition model. Okay, you can consider transition model as a function, okay, which you will apply on a state, okay, and action. Okay, so if you apply this action on this state, you will get another state, new state. Okay, so that will be defined by a transition model. So for example, if I move this 6 tile to this place, I am getting this configuration. Okay, so what is my transition function here? So if I apply right action on this configuration, I am getting this configuration. Okay, so that is a transition model. Next component is a goal test. Goal test. So goal test will be a Boolean function Boolean function. So you can apply. So for example, let's say this is a S0 and that one was the S1 state. Okay, so you can apply that test on that state. Okay, if that state is your goal state, it will return a true. Now S0 is not our goal state, so it will return a false. Okay, so it will compare a current state with the goal state. If it matches, then it will return a true. That is a goal test. The next one is the path cost. Path cost. So this path cost will assign a numerical cost to each state taken in the solution. Okay, so for a given problem there can be multiple paths. Okay, and your goal may lie on multiple paths. Okay, so this path cost will assign a numerical cost to that particular path. Okay, so in order to find a optimal path, we'll compare the path cost of these multiple solutions. Okay, and you will select the solution with the minimum path cost. Okay, so that is also required. So we can define a problem using these 5 components. That is the initial state. What is the initial configuration? Initial configuration of the problem. The next one, what are the possible actions available with the agent? Next one is the transition model. Okay, so if you apply a particular action, so it will define which. So it is just like a function. Okay, so function state comma action, it will return a new state. Okay, the next one is the goal test. Okay, it compares whether the current state is a goal state or not. Then last one is the path cost. Okay, which will give you the numerical cost of that particular path. Okay, now we'll try to define multiple problems. So consider first example. So first example is our vacuum cleaner world. Okay. So what is the scenario here? We have 2 blocks here named A and B, and we have a vacuum cleaner as our agent. Okay, and it has a sensor to sense whether dirt is present on the floor. Okay, if it senses a dirt on the floor, it can issue a command called suck, and that floor will be cleaned. And it can move to and fro between these blocks. Okay, so now we'll try to define this problem. Okay, so first one should be initial state. Okay, first let us find out how many states are possible in this problem. Okay, so we'll draw the state space for this problem. Okay, so now dirt may be present in both the blocks. Okay, and we can have agent here or here. Okay, so this little dot represents dirt. Okay, so if we issue a right command, okay, we'll get this state. Okay, if this vacuum cleaner moves to right, we'll get this state. If it issues left here, it will get this state. Okay, if it issues right command here, it will have no effect, right? It will be a same state. If we apply a left here, we are getting the same state. Okay, but if we apply a suck operation here, so this floor will be cleaned, right? So we will get this state. Okay, if we apply a suck command here, okay, so agent will be here, okay, and we'll get this state. Now if we apply a right command here, so we'll get this state, and if we apply a left command here, we'll get this state. Okay, now if the agent issues suck command here, we'll get this configuration. If we apply state here, suck operation here, we'll get this state. Okay, so every state is different here, so total 8 states are possible. 8 possible states. and we can draw a DFA from this. DFA, that is this deterministic finite automata. For every state we can issue 3 commands: left, right and sub. Okay, so we have 3 commands for this state: right, left and sub. Left, sub and right. Okay, let us complete this diagram. So right is done, left. If you issue a left command here, you will get this one, and if you issue sub command here, so there is no dot, so we will get same state. Okay, it will have no effect here. Okay, so now if we issue a left command here, we will get this configuration. Okay, if you issue a right command here, we will get the same state, and S is done. Okay, then if you issue a right command here, we are getting this state. If you issue a left command here, we are getting the same state here. Okay, if you issue a right command here, same state, and sub also same state. Okay, if you issue a sub command here, so we will get the same state. Okay, if you issue a left command, okay, we will get the same state. Okay, and right, what about right? So we will move to this side. If you issue a right command here, yes, if you issue a left command here, we will get this state. Okay, and what about right command? We will get same state and S. Okay, so now we have a complete DFA for this problem. Okay, so now let us define this problem. Okay, so what was the first component? That is the initial state. Initial state. What can be the initial state of this problem? Any state, one of this, all the 8 possible states can be designated as the initial state. Okay, let us name this states S0, S1, S2, S3, S4, S5, S6 and S7. So any state out of this possible can be an initial state. Okay, we can start from any state. Okay, next one is what are the possible actions here? So we can issue a left command, we can issue a right command, we can issue a sub command. These are the possible actions here. The next one is the transition model. Transition model. So what was the transition model? It defines like this, right? Okay, so if you apply for this diagram, if you apply right command on S2, if you apply right command on S2, I am getting S3. Okay, so this transition diagram defines the transition model for this problem. Okay, so transition model, if you apply a particular action on a particular state, you will get a new state. Okay, the next one is the goal test. Okay, goal test will check whether all the blocks are clean or not. Okay, all blocks are clean or not. So okay, so we should get either S6 or S7 state. Okay, the next one is path cost. Okay, so path cost is the problem dependent. Okay, so we can define here for every action, let us consider there will be 1 unit cost. There will be 1 unit cost. So for example, if we start with the S2, if you start with the S2, the path cost will be 1 and 2. Okay, that is one solution. Another solution will be 1, 2, 3, 4. Okay, so there can be multiple solutions possible. Okay, and optimal solution will be the solution with the minimum path cost. Okay. Okay, let us see the second example. Okay, so as this is a revision class, we will not see all the problems given in the textbook. So I think this missionary problem is little bit complicated. So let's cover that problem. So so this is 3 missionary and 3 cannibals problem. So what is the scenario here? So we have 3 missionaries. Okay. So let us represent missionaries by a circle and cannibals by a cross. Okay. So we have three missionaries and three cannibals on one side of the river. This is river, and we have a boat which at most can carry two people. Okay, so it may carry one people or two people. Okay, our aim is to take these people on the other side of the river. Okay, but the condition is that if the number of cannibals becomes more than the number of missionaries, then those cannibals can kill those missionaries. For example, at certain stage, if you arrive at this stage, this cannibal can kill this missionary. Okay, so you have to ensure that the number of missionaries should be greater than the number of cannibals. Okay. So let us define this problem. So first one is initial state. Initial state. So how to represent the state of this problem? So we can draw this diagram. Okay. So this will be the initial state. So there will be three missionaries and three cannibals on the left bank of the river, and there will be a boat on the left side of the river. Okay, but this is little bit complicated representation. So we'll find out the easy way to represent this problem. Okay, so we will use this tuple: number of missionaries, number of cannibals, and position of a boat. This representation to represent the state of the problem. Okay, so now the current state of this problem is three missionaries, three cannibals, and boat is on the left side. Okay, so this is representing the state of the left bank of the river. Okay, so there are three missionaries, three cannibals, and boat is on the left side of the bank. Okay, so initial state will be this one, 3 Okay, so what is my notation here? So number of missionaries, number of cannibals, and position of boat. Okay. Next one is action. Okay. What are the set of actions available here? Okay. So which action are we performing here? So we are moving missionaries or cannibals through a boat, right? So, and this boat can carry at max two people. Okay. So we'll use this notation here, this tuple here. So number of missionaries and number of cannibals. So this represent 2, 0 represent two missionaries are traveling. And then two cannibals can travel. Then one missionary and one cannibals can travel. Then one missionary can travel, and only one cannibal can travel. So these are the possible actions here. Okay. And then next one is transition model. Okay. So for that we have to find all the possible states here. So how many states are possible? Okay. So we can have 3L. Okay. Then 3-2L. Then 3-1L. Then 3-0L. Right? 3 missionary, 0 cannibal, and boat on the left side. Then we can have 2-3L. All possible combination. Then 1-3L, then 1-2L, then 1-1L, 1-0L, then 0. Okay. So for these cases, the boat was on the left side. Similarly, we can have boat on the right side of the river. So these many 32 states are possible here. Okay, so out of this, some are not favorable. Okay, so this one. So for this, there are 2 missionaries and 3 cannibals. So number of cannibals are more. So this is not favorable. Then this one is also not favorable because 2 1 on the left side. So there will be 1 3 on the right side, right? So 3 cannibals can kill that one cannibal. Sorry, missionary. Okay, this one is okay because there will be 1 3 there, right? Okay. So next one. This one is also not possible. This one is not favorable. And what about this one? Okay, 1 1. So there will be 2 2 on the right side, right? Then this one, 1 on the left. Okay. Yes, this is also not favorable. So okay. And this, what about this? 3 missionaries will be on the right side. Okay, they are together, so they are safe, right? Okay. So these many are not possible, not favorable. So similarly, we cannot have this one, then this one, same. This one, 1 3, 1 2, and 1 0. Okay. And actually, this state is not possible because we are starting with the board on the left side. Okay. So board alone cannot go on the right side. So this is also not possible. Okay. So actually we are not bothered about finding the solution here, but for this problem we will find the solution. Okay. So now our initial state is this one. This is our initial state. And what is our goal state? Goal state will be this one. What it represents? 0 0 R. Actually we are representing the state of the left bank, right? So 0 0 R. What it represents? There are 0 missionaries, 0 cannibals, and both on the right side, right? This indicates this configuration, right? That is our actual aim, right? So this is our goal state. Okay, so how to reach from this to this state? Okay, so if we take 2 cannibals on the right side, okay, 2 cannibals, so our command will be 0, this one, right? 2 cannibals are traveling, so boat will travel to the right side, and on the left side we will have this one. Okay, so I will represent here. So okay, 2 travel here, so okay, so 3 1 3 1, and boat is on the right side. Okay, now one should come here, okay, to get the boat on the right side. So it will become like this. So one will come back with the boat. Okay, again 2 cannibals will move. Again 2 cannibals will move. So on the left side there are 0 0 0. 3 missionaries and 0 cannibals. Okay, and one should come back. One should come back, so we will reach to this state. So one is coming back. Okay, so we will have this configuration. Okay, at the same time, this is the configuration on the right side. Okay, now 2 missionaries will travel. So this is the case. Okay, so on the 1 1 R. So we will jump to this state. So 2 0. Okay, 2 missionaries are traveling now. Okay, now if we move 2 cannibals here, so it will become 3 cannibals on the left side, and they can kill that person, that missionary, right? Okay, so we'll move this one, so we'll get XX 0 0. Okay, and on this side we will have 0x. Okay, so 1 1 will travel. 1 1 will travel, so we will get 2 2 L. Okay. Now 2 missionaries can travel. 2 missionaries can travel. So 0 0. Now 3 missionaries will be here. Okay, and 2 cannibals here. Okay. Okay. So 2 missionaries can travel. So we'll get this state 2 0. Okay, 0 missionary on the 0 missionary on the left side and 2 cannibals and both on the right side. Okay. Then one cannibal will move this side. Okay, we'll get 0 3 configuration 0 3 and 0 3 L. So one cannibal will take the boat on the other side. Then then 0 2. Then two missionaries will travel. So one will be here and we will get this one. Okay, and then one. Okay, two missionaries. One missionary will come here. So we'll have this configuration 0 1, and then finally these two can travel. Okay, so there will be XX, and then finally two XX will be travel, and we will have this one and both on the right side. Okay, so this is a transition diagram. This is one of the solutions. There can be multiple solutions possible. This is the optimal solution. Okay, so transition model is this one. Okay, for any state, if you apply a possible action on that, you will get a new state. Okay. Next one, transition model is done. Then next one is goal test. Okay, so our goal state is 0 0 and R. Okay, and then last one is path cost. So we can define 1 unit cost for each movement. Okay, so path cost for this solution is 1 2 3 4 5 6 7 8 9 10 11. Okay, so 11. There can be multiple solutions with other path cost. Okay, so this is regarding 3 missionaries and 3 cannibals. So this is the problem definition for this 3 missionaries and 3 cannibals. Okay, so if you define a problem using these 5 components, that problem will be clear to the solver. Okay, it will be unambiguous. Okay, you will cover all the possible aspects of that problem. Okay. Okay. Now, as a homework problem, you try to solve, try to write problem formulation of TSP problem. What is TSP problem? That is traveling salesman problem. It is a touring problem where you have to visit every city exactly once. Okay, that is traveling salesman problem. You have to write the problem formulation for that, and then you write problem formulation for 8-pin problem. 8-pin problem. Okay. So these are the homework problems. Next topic is search strategy. Okay. So what is search strategy? It is nothing but search algorithms. So consider again this 8 puzzle problem. Okay, so what is 8 puzzle problem? So we have 3x3 grid here. Okay, and we have a tile, and every tile is assigned a particular number. Okay, so at the starting it may be a random configuration. So we will see this one. Okay, so this is the initial state of the problem. Okay, so now we can move this, we can slide these tiles. Okay, and other player will give you the goal state. Okay, so for it may give you this goal. you have to arrange the tile in this fashion. Okay, so you can slide these tiles and you have to reach to this. So this is initial state and this is goal state. Okay, so now, so initial state is over. The next one is the what are the possible actions? Okay, so every tile can move left, right, up and down. Okay, and we have 8 tiles here. So 8 multiplied by 4. So total 32 actions are possible. Okay, but can we reduce the number of actions? Yes, definitely. Because consider this tile L. If you move this 7, if you move this 7 tile here, actually this space is moving towards the left. Okay, if you move this 8 on the left side, the space will move towards right side. Okay, so instead of mentioning the action in terms of a slide, we can define the action in terms of the movement of the space. Okay, that space can move to the left, right, up and down. Okay, so from this configuration, if I apply left, I will get this configuration. So now we are talking about movement of the space now. So if space is moving towards left, 7 will come here. Okay, and other will remain as it is. Okay, if we issue R command, that is right command, okay, so space is moving towards right. Okay, so 8 will come here. Okay, and then up. If space is moving up, then 1 will come here. And then next one is down. Okay, 3 will come here. 4, 1, 2, 7, 8, 6, 5. Okay, then now from this space cannot move to the left, right? So it can have only 3 actions. So that is right, up and down. If you issue a right command here, what we are getting? We are getting a same configuration. Okay, so while searching, you may fall in a loop. Okay, so in search, so some path may be infinite. Okay, then you have to continue like this, and what we are getting a tree-like structure. That tree is known as a search tree. Okay, and every node, so this collection of a node forms the state space of the problem. Okay, collection of these nodes will be a state space of a problem. Okay, the next one. Okay, so now the root of this tree will be our initial state. Okay, and what are the branches? Our possible actions are the branches of this tree. Okay, next one. Okay, so down the line we may reach to the goal state, and if you backtrack that branch, you will get the solution to that problem. Okay, so now we are talking about the search strategy here. Okay, so the search strategy depends on how you traverse through this tree. Okay, if you travel level by level, that will become a BFS algorithm, breadth first search. So base first search, breadth first search. So the pattern will be like this. In BFS, it will be like this. Okay, you will travel level by level. Next strategy is DFS. So if you travel to the deepest of that particular branch, okay, deepest level of that particular branch, and if solution is not there, you will backtrack to the other possible branch. That is the DFS, that is depth first search. Okay, so the way you traverse through this tree decides your search strategy. Okay. Okay. So next topic is expansion and generation. So what do you mean by expansion and generation? Now consider you have reached to this state. Okay, so now three actions are possible here. You can move right, up and down. Okay, if you apply this action on this state, you are generating new state. Okay, and you are expanding that state. Okay, so if you apply this actions on this state, this gate is getting expanded, and these three states are getting generated. Okay, so remember this terminology, expanded and generated.